Recording is rolling. It is Friday, January 10. You guys have your lab pages out. All right, so recap what's going on. You guys remember yesterday we were on this side of the lab page. Looks like a seesaw. Okay. You guys have the same materials on your desk today as you did yesterday. Today as you did yesterday. There's meter stick, there's spring scales, there's lab weights. You guys got all that. Okay. And today, flip this over, we're going to do the scaffold side. Also, I have an example of scaffold here, so I'll do an example with you guys, and I have a few PowerPoint slides to show some extension examples. Right? And so we'll be doing all this. Right? Oh, I'm going to show you. Sorry. Oh, I'm going to start here, guys. Let's look up here. We'll do a recap of what you guys did yesterday, because I was trying to design this so that it was fundamental and easy to understand and follow, but there's a lot of little boxes, and a lot of students yesterday got kind of stuck in the weeds of following a lot of little boxes and figuring out like what meant what. But at the core principle, it's just this. Guys, torque. Guys, look at here. Torque. Torque is what times what? Force crossed with lever arm, right? Or R cross F, I should say. Right? So open a door, turn a wrench, right? So if you pick a pivot point like on the right side here, or side of the slab, if you pick this spring scale as the pivot point, then this lab weight was trying to turn it how? Clockwise or counterclockwise? Clockwise. And on the left side, this is turning how? Counterclockwise. But what does the torque have to sum to for equilibrium? 0. And so you had all these considerations. The meter stick also had a little bit of weight, could cause some torque, right? Unless you had it parked right, where the pivot point was. Right. So if you considered all the torque except for the mystery weight, then it came out to some amount. Therefore, the mystery weight itself, and that was the goal yesterday, to figure out what is this mystery weight? Same goal today when we get to that side eventually, right? Has to be causing amount of torque to zero that out. So negative 130 plus 130 zeros out. This is in Newton centimeters. Okay. And if you know the location, like this radial arm could be 28 centimeters, was my example yesterday. If you take this torque divided by radial arm, you should get the force. And if I was hanging on a 5 Newton lab weight, I hope that force comes out to 5 Newtons. Got 4.6. That's really, really close. So I'm good with that because 4.6 is really close to 5. Right? You guys remember that? Then what I had you guys do about the last 5-10 minutes of class yesterday was not change your setup. You could have the same weights, the same positions, the same, but change your perspective. You guys see I circled up here? Instead of doing pivot point scale, we're doing pivot point 0 centimeter mark. You guys remember that? All you did was change your perspective. Because what I was trying to show you guys was that the torque sums to 0 regardless of what you define as the pivot point. So this end of the meter stick at the 0 centimeter mark is a completely random point. Okay? And from this point of view, here's what I forgot to do yesterday. I'll do it right here as part of the review. Okay? Guys, if this is the pivot point, if this is your door hinge, then this weight on the left side is now causing what kind of torque? Clockwise or counterclockwise? Clockwise relative to this endpoint. Okay? And the meter stick itself has a little bit of weight, which we're calling 1.2 newtons. Okay, so that's causing a little bit of a clockwise torque. The spring scale is holding back everything. How? Clockwise or counterclockwise? That was your counterclockwise right there. Okay, and then this lab weight on the end was probably a pretty big clockwise torque because it's such a huge distance all the way to the right. Okay. And again, it was mystery weight, so you were solving for this force given everything else. So you know the reading on the spring scale, you know the weight of the meter stick, you know the left weight. You're allowed to know all those numbers, and you know the distances from the 0 centimeter mark because very conveniently they're just whatever numbers on the meter stick. Okay, but this is at 90 centimeters out from 0. 90 minus 0 is just 90. Okay, and then same process. Now I have 4 torques. If I add 3 of those torques together, I get some number. The 4th torque must zero that out. So I got negative 370 versus 370. If it was at 78 centimeters out, divide that. And then, oh, look at there. I got almost 5 newtons again. Again, that's yesterday, but that's just a little bit of review. Okay, you guys remember that? Okay. All right, that was what you did yesterday. Now today we're going to flip over and do the scaffold look inside. Right, scaffold look inside. Right. Now before we dig into this, because again, there's a lot of little boxes. Guys, this is one of those labs. If you see the big picture of how this works, then everything pops into place, and it's not that bad. If you don't know the big principle and you're just like focused on box by box by box, then you can get lost in the weeds really easily. Okay, and then it's hard to get anything out of this. Okay, so let's focus on the big principle. So what I want to do is take a break from this for a moment. I want to do a little bit different example with you guys, and I'll show you guys a few PowerPoint slides, and we'll come back to this and I'll do an example with you guys. Okay, all right, so show you guys exactly what to do with this lab. So let's do this. I got this stripped down. This is a really nice fundamental example. You guys see this guy walking on the scaffold beam? He's just walking back and forth on the scaffold. Right? And it's held up by a couple of ropes. Hey, this is the Paul Hewitt example. You guys remember Paul Hewitt was a sign painter for a while? He was walking back and forth on the scaffold. If Paul Hewitt walks from left to right, what is happening to the tension in this rope as he walks to the right? It's getting more and more. It's increasing, isn't it? What if he has a friend sign painter? He's like twinging it as he's walking. It sounds like this. Boing, 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 boing. You see that? If he walks away, back to the left, boing, 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 boing. Okay, you see that? Okay. So these tensions are changing. Now, guys, do these two tensions collectively have to hold up his weight? Yeah, right. But what are they individually is a question that you cannot solve with forces alone. Last semester, I told you force equilibrium. So, okay, if the force is up, balance with the force is down. Right, that was last semester. Right. Starting this week, you have to say, well, depending on its location, each individual force can be different. Okay? And that's a torque question. So how do you solve this? Okay? I want you guys to see that I did make this really, really fundamental. Notice the beam itself, I have negligible mass, which means it has negligible weight. So I'm going to ignore that. So the only weight that matters is the weight of this guy, which is 100 newtons. Okay? The beam has a length of 10 meters. This guy's standing 7 meters over from the left side, and I got 2 ropes holding that. Okay, so you guys ready to solve this? So here's my 2 conditions for equilibrium. Let's spell that out. Equilibrium. My 2 conditions are, actually, maybe you guys tell me, guys, what's one of my 2 conditions for equilibrium? The sum of what goes to what? Aha! The sum of the forces goes to 0 newtons. Okay. And since these are 3 vertical forces, maybe I'll throw in a little subscript y, like in the vertical direction. Okay. And what's the other condition? The sum of what goes to what? Torque goes to 0 Newton meters. Okay. Because you guys remember torque is R cross F. You guys remember that? Okay. Radial arm cross with the force. You guys remember that? Okay. All right. Now, one of the things, of course, I want you guys to get between yesterday and today is you don't have to pick any particular point as the pivot point. The torque will still sum to 0 regardless, right? But a lot of times there's an intuitive pivot point to pick or one that's mathematically works out really nicely. Okay? For example, you can solve this in one equation or solve one of the force tensions anyway. Right? If you pick, here, guys, watch this trick. Right now, this is a little trick. If I pick the far left end as the pivot point, watch what happens. How much torque does the left tension cause about the point where it's acting at? 0 torque. And I can show that to you here in class. I'm going to walk over to the store. If you're watching this video at home, then use your imagination. Walk over to the door, and I'm pressing on the hinges. I'm trying to open the door. I got to get out of this room. And I press it really hard on the hinges. Is this ever going to turn the door? No, because I'm causing 0 torque about those hinges. Okay? So what that means is if I pick this point as the pivot point, that mathematically this left tension is just going to go away out of the equations, which means I'm only going to have one unknown left in my equation. You guys see right now as we're looking at this, there are 2 unknowns because I don't know either one of these tensions. Right? Guys, if you have 2 unknowns, how many equations do you need to solve that? 2. Right? Can you solve 2 unknowns with just one equation? No, you need 2 equations for 2 unknowns. Right? But if I define this as my pivot point, then this left tension causes 0 torque, right? Which narrows it down to just one unknown. I can solve that in one equation. Right? You guys want to see how that works? Right? So I'm picking, here's my condition right here. So my torque goes to 0. I'm going to pick the left end as the pivot point. Okay. And I'm going to say from that point, at 7 meters is 100 newtons. So R cross F. So 7 meters out is 100 newtons weight. Okay. Now I do have to pick a convention for positive or negative. I'm going to call clockwise negative. By default, you tend to. Right? So I'll make this a negative torque. Or maybe I could call it negative force and it comes out negative. Right? Heads up, I don't know why I did this, but on your lab paper, I did reverse that convention. So on your lab paper, I set it up so that clockwise is positive. Okay, so just kind of look at that. Okay. But here I'm doing more textbook. Right? Right, then plus, right, then at 10 meters out, acts the tension on the right side. So 10 meters is, and I don't know what that is, so I'll just call it TR, tension on the right side. So for that. Okay. You guys, if I add all that up, it sums to how much? 0. Yeah, 0 Newton meters. Okay. So let's see, I got 700 Newton meters here. Can add that over. So 10 here. So 10 meters times tension on the right side, which I'm solving for, equals 700 Newton meters. Divide both sides by 10 meters. The tension on the right side is 70 newtons. That's right, 70 newtons. Okay. Next question is, if the tension in the right rope is 70 newtons, how much is the tension in the left rope? Huh? Here, let's go back to this condition right here. You guys remember force equilibrium? The sum of the forces goes to zero, right? I have 100 newtons down. I know there's 70 newtons up here. So what does the left side have to be? 30. Do you guys see the tension on the left side has to be 30 newtons? Do you guys see that? Because 70 and 30 up is 100. This guy weighs 100, he's pulling down 100. 100 up, 100 down, zeroes out, matches this condition. The other way you could have solved the tension on the right side is you could have set up a different torque equation, maybe change the pivot point to like over here. Okay, there's it. Okay. All right. What's going to say about this? Do you guys see a nice shortcut rule of thumb? If you have a very nice simplified version, again, the beam doesn't weigh anything in my example, only the guy does. The two ropes are at the far ends, and they're both pulling in exactly vertical. So for that very special case, do you guys see that the tension in each rope is very simply proportional to his distance from the end? The fact that he's 70% of the way over, the tension on the right side holds 70% of his weight. Is that? That's a nice little shortcut. Okay? Now, you could make this more complicated, and maybe you have to be careful about that shortcut, but for something very simple like this. Okay? Are we good? All right. So let's do a few PowerPoint slides. This view here. All right. So all right, here's the lab you guys did yesterday with the seesaw. All right, we just did a quick review on that earlier today. That was yesterday's lab. Okay. Today's lab looks more like this. Okay. You'll be holding this up with two spring scales, so this is going to be a lot more balanced. See, yesterday with the seesaw was a lot more tenuous, right? It was really hard to balance it, but today is definitely going to be balanced. Got two spring scales holding up. You're going to put some weight on, and the goal of today is to calculate that lab weight. Suppose it's like a mystery weight based on these measurements. Okay. Your meter stick weighs a little bit, so we'll consider that. And look at these two boxes down here. I have the two conditions set up to solve this for equilibrium. The sum of forces goes to zero, the two tensions up, and the two weights down, zero out. And the other condition, which is the very bottom box, is the torque sums to zero. See if you guys can read the music of this equation. Who could tell me, based on how I wrote this very bottom equation, there's like 10 different ways I could have written this bottom equation. Okay? Who could tell me, based on how I did write it, which point did I pick as the pivot point on this picture? The left end point. Yeah, exactly like my example I just did anyway. See where my mouse cursor is? That is the pivot point according to how I set up this equation. Because the left side tension is 0 meters from itself, and then everything follows in place. Okay. Weight of the beam, L over 2. Oh, speaking of that, actually, this is something we did yesterday. I didn't emphasize this point very much, though. Do you guys think the weight of the beam is actually distributed over the entire length of the beam? Yeah. Is it okay mathematically to treat the weight of the beam as a single point at the very center, at the center of mass? Yeah, which is what we did yesterday, and we'll do the same thing today. Okay. All right, so that's why it said L over 2. All right. This object is at some distance x, and tension right is at the full distance L away from. Okay. So that's why that equation looks like. And all zeros out. All right, what else we got? Okay, so lab table from yesterday, lab table from today, where you guys are about to do in a few minutes. Okay. All right, let's look at some variations on this. This right here is a classic physics question I've seen pop up in a number of physics textbooks. If you take physics in college, good chance you're going to get this question. There's a ladder resting against a frictionless wall. So there's no friction against the wall, but maybe there's friction from the floor. In fact, there better be, otherwise it wouldn't stay up. Okay. A classic question could be, what's the minimum coefficient of friction to make sure the ladder doesn't fall down? Right? Or you could ask a different question like, if you know the coefficient of friction between the ladder and the floor, can you figure out what's the maximum angle they could rest on? So you could ask that too. Okay? Right. But regardless of the exact question, here's your conditions to solve it. The sum of the forces along each axis goes to zero, x direction, y direction, so horizontally and vertically goes to zero, and the torque goes to zero. And you can't solve this without also considering torque. Okay? And a good trick, kind of like I just told you a minute ago, is you guys see down at the bottom of the ladder where the ladder touches the floor? If you pick that point as the pivot point for all your math, then very conveniently, two of those forces immediately zero out from your torque equation, because it's like pressing on the door hinges. Okay? And that just narrows down to two other forces to cause torque, which is what I did in this very bottom box right here. Okay. What else we got? Do you guys see this beam being held up by this cable? So cable on the right side and maybe this joint on the left side. Except I drew in all the forces, free body diagram, got all that right there. Sometimes called force diagram. Okay. And a classic question could be, what's the tension in the cable? Right? Or if you know the maximum tension, could you solve for something like that? Right? One of your textbook questions from your chapter 8 questions is going to be pretty much this. You can also, I think they threw a little flag or a little banner, right, which might have a little bit of weight on it. So that could be this plus a little bit more complex. My AP students have a picture that looks just like this, except they have a hungry bear, and there's a hungry bear that's like walking across this beam, and there's a basket of goodies down here. And as the bear walks to the right, the tension, guys, as the bear walks to the right, what do you think happens to the tension in this cable? It increases. And if there's some maximum tension before it snaps, do you think there's some maximum distance that the hungry bear can walk out? Right. So that's for my AP students. But here's the nice fundamental basic version. Right? So you can set up a torque equation there. Okay. Okay, I have a bunch more slides, but these are all getting into angular momentum. So I'm going to save these for, well, next week probably. All right. So let's scroll back to, here's your setup today. Right. So setup today. All right, so let's take a look at this lab paper. Can help you guys out here. All right, so now we're on to this. Right, so we got the scaffold set up, got a couple of spring scales you're using to hold up, right? And we have one weight today, so just one weight. Right? Now the goal of this lab, give you guys something to solve for, is can you calculate what this weight is? Obviously, you're going to know what it is. Like, guys, if I hang this 500 grams on, how many newtons of weight is that again? 5 newtons. Okay. Do you guys think the answer to this should be 5 newtons if I do everything correct? Or pretty close. If it's like 4.7 or 5.1, that's plenty close enough. Right? All right. So can you solve this with torque? Right. Now, again, if you can see the big picture, then all these boxes will just pop in place. Do you guys see on the right side? I'll start with the right side, just like yesterday. It says pivot point F left. That's like, bam, this point right here. I just put a giant X on. That's your pivot point. If that's your pivot point, then how much torque is caused by the spring scale at that point? 0. Is there any question why this box says 0 Newton centimeters? Right? Because whatever the force is, it's at the location of itself, right? Which is zero torque. About the point. That's why I typed in 0. Okay. The weight of the meter stick. Ooh, okay, here's a number that I do need to give to you guys. Do you guys remember from yesterday what the weight of the meter stick is? 1.2 newtons. Let's do 1.2 newtons. Okay, that might not be 100% accurate. So if this doesn't work out 100% accurately, then well, let's call that my fault. It's probably that number right there. Okay, but it's really close. Okay, and the weight of the meter stick is causing what kind of torque, clockwise or counterclockwise? Clockwise, right, relative to this pivot point. Okay. Okay. Do you guys see the radial arm is right here? And it says exactly. It says X meter stick, which is at the 50 mark. Right, because isn't the weight of the meter stick, we're going to treat it being at the 50 centimeter mark, right? Minus whatever this is. If this is, guys, if this is at 10 centimeters, and this is at 50, what's 50 minus 10? And that would be the number that goes in this box, right? That might not be exactly your numbers, but just get the idea, right? Right, and you can get the torque out of that. The weight itself, the mystery weight, is not causing a huge clockwise torque. And this right spring scale is causing what kind of torque? Counterclockwise, right? So since this torque goes to 0, I have 3 other torques. So I got 0 torque here, and this torque, and this torque, and I'll add up. Let's say I get like negative 95 units. I'm just making something up. Because if I get negative 95 units here, what does the final torque have to be? Positive 95. Because what's negative 95 plus positive 95? 0. And that's the guiding principle for this whole lab, is equilibrium. Right? Is 0 Newton meters. That's what we did before. That's what I did on the PowerPoint slides. It's you've seen over and over. Right? Torque comes to some 0. Then if you know the location of this mystery weight, here, let's do an example. Okay, suppose this is at 70 centimeters and your pivot's at 10. What's the difference between 70 and 10? 60, and that would feed down right here, wouldn't it? Okay, I'm just making something up. Okay? And then you could solve for this F, do this torque divided by this radial arm, and get this force. And hopefully it's really, really close to what you actually hang on it. You guys get that premise? All right, one last detail. Oh, the last part of this lab, see, you're switching perspective. You can leave everything exactly where it is. You don't have to change anything about your setup except your perspective. I'm going to switch my pivot point to this 0 centimeter mark. Bam, right there. Because again, I want you guys to see that in principle, you pick any point as the pivot point, torque still sums to 0, so therefore you can still solve the mystery weight. Okay? Right. Now, relative to this point, now the left-hand scale is causing a what kind of torque? Clockwise or counterclockwise? Counterclockwise, right? Right. Now, this is we're definitely in abstract territory here, right? But so you have to really use your imagination. This is really a mathematical exercise, right? So relative to the 0 centimeter mark, this would be like if this was a door hinge, this would definitely pulling counterclockwise, right? The weight of the meter stick again clockwise a little bit, the mystery weight clockwise, and this right end scale is pulling hugely counterclockwise. Now we definitely have 1, 2, 3, 4 torques. You guys see 4 torques, right? If you add 3 of those, you're going to get some number, like maybe like negative 85, and therefore the final torque has to be positive 85 to zero it out. Right? Divided by the location, radial location, right? Which everything minus 0 is just its location on the meter stick. Right? That should also give you the mystery weight. Right? You guys get that? All right. So, you guys got the rest of the class to do this. Now, this is the long class, so you guys have a little extra time. My other classes, we've had about 20 minutes, which has been just enough time. If you keep a pretty good pace, then you should be able to finish this in class. If you do, then pop this in the grade tray. I'll give you guys points. Some students have not finished. If you don't quite finish, then at least get the recordings marked to get all the forces and the locations. If you have to do the torque calculation over the weekend, then you can bring that in on Monday. But if you keep a pretty good pace, then I think you'll be able to finish that today.